In the previous video, we installed Node.js and created our first simple application with it. Now, in this video, before we move on any further, I want to take some time and reflect upon what exactly Node.js is. What this thing really is that we're trying to get ourselves into. Now, we could just cut the conversation right now and say that Node.js is an asynchronous event-driven JavaScript runtime, or Node.js is a JavaScript runtime built on Chrome's V8 JavaScript engine, but unfortunately, that probably doesn't make any sense. We have a lot of words that we're not familiar with. We have JavaScript engine. What is this JavaScript engine? What is event-driven? What is asynchronous? And what is V8? And even, what is really JavaScript itself? So now, we're going to have a long discussion answering these questions. We need to see how Node was created, what sort of problems it solves that JavaScript otherwise couldn't solve, and what do we mean by these strange words that we have on the screen. And just a quick disclaimer, in this video we're going to dive into the Node source code and have some fun. And we'll also see some C++ code, but you don't need to know C++ at all. As long as you can understand the comments that I'm going to write, you are absolutely fine. Just watch the video and you don't even have to follow along and do the things I do. And our discussion would probably be kind of long, and if at any point you feel lost, confused, and you're telling yourself, hey, why exactly are we doing these? I just want to learn Node. Well, please just bear with me till the end of the video and trust me on this one. You're going to see and realize the importance of this discussion as we move along with the course. It's really important to first see what Node.js really is. Okay, let's start from the minimum, from the very basics. Processors can only understand machine code. Now, I want to use the terms microprocessors, CPUs, or processors interchangeably, but they have some differences, and for our purposes, it doesn't matter, and we will refer to them as the same thing. So these processors could only understand machine code. And each processor has their own unique language. And we have different processor architecture, and each one of these architectures could only understand their own language. So we have architectures like ARM46, MIMS, x86, and a couple more. So each one of these have their own language. So a manufacturer of a processor might say that, hey, this is how we could talk to my processor. For example, if you want to tell it to add two numbers together, here's how you could do it with the available instructions that it has. And actually, machine code is just zeros and ones. Now, for the sake of simplicity, we usually use some codes and hexadecimal numbers instead of just writing straight zeros and ones, but ultimately, they're just zeros and ones. A CPU already knows that, for example, if I get the character XR, it might mean this specific zeros and ones. And in the real world, you rarely need to write machine code, well, except if you want to create a compiler or you really just want to talk directly to the CPU. In most cases, using another language a little bit higher level is going to get your job done. Now, on top of machine code, we have assembly language, which is incredibly low level. And to convert an assembly code to machine code, we don't actually use a compiler. We use something called an assembler. And what it does is that it takes the code that you write and converts it straight to machine code or just zeros and ones. So we have some instructions, an assembler takes them and converts it exactly to the machine code for the specific processor that you're coding for. Then, if we go a level up, we have languages like C and C++. With these languages, you actually have access to the operating system and the hardware. So you have maximum amount of control over your memory, over, for example, if you want to go ahead and fetch something on the hard drive or go ahead and talk to the network card to, for example, send a request to the internet, you could use these languages. So you have a lot of control with C and C++, but the more control you have, the more responsibilities you have. So you have to be careful if you want to write code in C and C++, because you have so much control, you might mess some things up. And if you use C and C++, you need to use something called a compiler. Now, a compiler takes your code and converts it into an assembly language, and then it converts that assembly language using an assembler to machine code. Now, if we go a level up, we have very high-level programming languages like JavaScript and Python. Now, these are incredibly high level, and usually with these languages, you don't have access to the hardware. For example, with JavaScript, you can't just access files. You can't send a network request, because to do those things, you need to be able to talk to the hardware, and with these languages, you can't do that. Now with C and C++, you could really create anything that you want, be it an operating system. If you want to go ahead and create, I don't know, for example, Linux or Android from scratch, you're going to be just fine with just C and assembly language. You're not going to need to write machine code so much. Well, maybe in very rare cases, but using just assembly and C, you could literally do anything that you want. Now, for some very complex applications like video editing applications or photo editing applications, they need to have maximum amount of control over hardware and they need to have maximum amount of performance. Those are usually written in C and C++. But in a lot of cases, you don't actually need to have access to that much control and power, and you're going to be just fine creating your application in JavaScript, Python, or many other high-level programming languages. So we have kind of like this hierarchy in order to get to JavaScript. So now what I want to do is to show you two examples, one in assembly language and one in C++. But don't be scared, it's gonna be okay. I'm just gonna show you some code and you don't have to do anything. Just watch me do it. And I'm trying to make some points here, right? So let's first see the application written in assembly language. So here it is. I have created a folder on my desktop called assembly demo. And I have created a file called hello-world.s, which is an assembly file, and all it does is that it outputs a hello world message to the console. So that's all it does, just a hello world application in assembly. And if I open it, notice that it looks really crazy. Don't worry about the syntax, you don't have to understand anything here. Well, except a couple of things. First of all, this whole code, 20 lines of code, all it does is that it goes ahead and prints hello world out. Now, if you read the comments, you would kind of figure out what we're doing here. Here it says simpler program to print hello world. Then we're setting up some parameters to print hello world and telling the kernel, the operating system, to actually do it. Then we have some parameters here. We have this hello world. Think of it kind of like a variable. Then the length of our string, you even have to specify that one. Then here we're telling the operating system to actually do it. And right here we're setting up some parameters to exit the program. So you can't just write the code and say that's it. You have to specify how you want to exit. Then here's our final string, which is hello world. Now, notice here we have some hexadecimal numbers and character encodings, which are really important to understand, but we will talk about them in the buffer section and not right now. So yeah, that's it. Notice that we're doing a lot of things just to get a hello world out. And it's even a lot more work if we try to run it. Now, one last thing that I want to point out here is that when we want to run this application, when we want to run it through an assembler to get a binary executable file, all it does is that it converts these commands to just zeros and ones. So I might, for example, take this move and say, instead of move, put this one. Ultimately, this file would get converted into just zeros and ones. Now, let's go ahead and run it and see how much work that will take. So I want to open up my terminal. You don't have to do this, just follow along. And I want to paste in some commands. I'm not going to write them because it could be kind of long. I want to first run it through an assembler using the as command. I want to say that the output should be hello world.o, which is an object file, which you don't need to understand. Just think of it like an object file that we would give that again to the assembler, and then it's going to give us an executable file. And this is our input file, hello world.s. And if I run it, now I'll get this hello world.o, which is an object file. And the last command that I need to run, which is a lot longer, is this ld command. And the only two things that I want to say here is that we have to specify our operating system and also our CPU architecture. So you can't just say that I'm writing assembly code, just like the way you say I'm writing JavaScript code. You have to say I'm writing assembly code for this operating system and also for this CPU architecture. Because each operating system and each CPU architecture needs its own unique commands. For example, if I want to run this program, but for an Intel-based CPU, some of these might look different. But now let's go ahead and run it. And now I will get an executable file. So if I run this hello world, I'll get hello world. So this is our assembly application. Let's also take a look at the File Explorer just to see what we have. So we have our .s file, which is our assembly source code. And then we have the object code. And then we have a Unix executable file. I could just double click on this. And it's going to run it. And here's our hello world message. Alright, so that was our very simple assembly application. And now let's move up a little bit and talk about C and C++. Notice here that we're trying to ultimately get to JavaScript and Node.js, but we need to lay a foundation of knowledge before we get there. So what I want to do right now is to show you a simple C++ application, just like I did with the assembly language. And we're just trying to understand some simple things, okay? So here we go. So I have created a folder called File Creator, and inside of it I have a simple C++ file called filecreator.cpp. And if I open it, notice that it looks a lot more like JavaScript than assembly does. And what it does is that it asks me for a file name and some content, and then it goes ahead and create a file on my hard drive with that content and that file name. So here, just read the comments. This variable here determines whether we should continue creating files or exit. And then we have a while loop, just like JavaScript. Here's the variable that saves the name of the file, the content. Don't worry about the syntax here. And then here it asks for the file name, and then the content. And then here it creates the file. That's all. So this is a very simple C++ application. And now I'm going to go ahead and run it. So I'm going to open up my terminal, and the way we could run C++ is using a compiler. The compiler I use is called G++. So I'm going to use G++ and output a file called File Creator, and I want to give it the contents of this CPP file. Now I'm going to run it. And now, just like before, we have an executable file. I could double click on it, run it, and be able to create files. And now I'm going to go ahead and run the application, and all I need to do is to specify the executable file name in my terminal. So file creator, and I'll run it. Alright, so here it is. It has a very simple menu. I could either create a file or exit. I know it's a pretty silly application, but let's just stick with it and try to understand some things in C and C++, because JavaScript and Node.js are written in C++. And later on, when we get into the Node.js source code, we're going to have a much easier time understanding how things kind of work together if we have some understanding about C and C++. Okay, so let's just go ahead and create a file. Now it asks me for the file name. I have to specify the path along with it. So users Joseph desktop, and then I'm going to call it file1.txt. And then the content that I want to put in the file, just going to put, this is the first file. So the file was created successfully. I'm going to create one more file. I'm going to specify the same path, but I'm going to call it file2.txt. And this is the second file. And now I'm going to exit. Okay, so now if I go to my desktop, I could see that I have now two text files on my desktop. File 1, which contains the string, this is the first file, and also the file 2. This is the second file. So pretty simple, pretty easy, all right? But notice now that I have this executable file. I could just go ahead, double click on it, and I could run it. So if I open it, I could double click. Just like before with assembly language, we get a Unix executable file. I could run it and just specify the options and play around with it. Now, the interesting thing here is that I could now cut this file out, maybe put it on my hard drive or on my USB, then completely wipe out my computer, my laptop, and then be able to paste that file in back to my computer and be able to run it without needing to compile anything. So this is an application. I could move it around and run it, and everything's going to work just fine. But if I want to move this file to another laptop, I could even move it to another laptop that uses the same operating system and the same CPU architecture as I do, and that laptop is going to be able to run this file just fine. But I can't just take it to any laptop. If a laptop doesn't use the same operating system, perhaps it might be a Windows machine, or it doesn't have the same CPU architecture as I use. For example, it might have an Intel-based CPU. That laptop is not going to be able to run this file. So we have to get a different build for various different CPU architectures and different operating systems. Now remember that we said when you compile a C++ application, the compiler would take your C++ code and then it would convert that into assembly, and then an assembler would convert that assembly code into machine code. Now G++ is doing all of that behind the scenes. And if we want to see the assembly output of our C++ file, we could do so by running our compiler and specifying the -s command. And then my outputs, which is going to be file creator.s for assembly code and file creator for the executable file, and then the input. Now, if I go into Visual Studio Code, you could see that we have this .s file. And if I open it, notice that it looks kind of like before, that assembly file. It's actually an assembly file, so if I search for move, we have a lot of that commands here and there. So ultimately, your C++ application would get converted into an assembly file, and then this assembly would get converted into machine code. And if you're curious to know, this 15-line program got converted into more than how much? 8,000 lines of code. I know it's kind of crazy, but yeah, this is why we don't write assembly code and we use languages like C and C++, because writing all of these yourself just to be able to create some files is pretty crazy. But actually, one of the reasons that it's so long is because we're including some files, some C++ files. So if I just go ahead and create something extra simple, like something that defines a variable A and a variable B, and then add them together and save them in variable C like this. And if I get an assembly file off of this file, it's going to be a little bit simpler. Still, way more complicated than just these 3 lines of code. But you know, it's assembly language and you're talking directly to the CPU. Alright, now another fun thing we could do is to add this file, add this executable file to our path, so that we could always have access to our application by just running file creator. In fact, let me just go ahead and do that. If I want to do it, I need to add it to my path. So I'm going to go into my hard drive and then user local bin. Now I'm going to copy this file or cut it and move it to this bin folder. So I'm just going to move it like this. I want to put in my password, and now that I have it in my bin folder, I could just run file creator and be able to create files. Let's test it. So here's my desktop. I have 2 files. I'm gonna call it, let's put it on the desktop again. File 3.txt. And it's now created. Another one, file this.txt, and exit. Pretty cool, right? So at any point in time right now, I could just run that command and be able to create files. So we did a lot of talking, but now we're ready to talk about JavaScript and then Node.js. So let's see what's going to happen when you write and run JavaScript code. So as you know, JavaScript is a programming language, meaning when you write JavaScript, you're giving instructions to your computer to do something. be it adding some numbers together or modifying a string, sorting an array, etc. And you also know that computers could only understand zeros and ones. So in order to be able to run JavaScript, we need a way to be able to convert our code into machine code, something that computers could understand. So how do we do that? How do we get our code into that machine code? In assembly language, we saw that we use an assembler to convert our code into zeros and ones. In C++, we used G++, which is a compiler that converts our C++ code into machine code. Now, in JavaScript, we use a JavaScript engine to do that. JavaScript was first created by Brenton Eich in 1995. And he created this engine called SpiderMonkey, which was the first JavaScript engine ever. Brenton was working at Netscape at the time, which was owned by Mozilla, and then later Mozilla took that engine and used it on its web browser, Firefox. So Firefox now uses this JavaScript engine, SpiderMonkey. And ever since JavaScript was invented in that year, a lot more JavaScript engines were created. Actually, you could create your own engine too, something that could take JavaScript code and convert it into something that computers could understand. Now, a JavaScript engine that we're going to talk about, and Node.js and Google Chrome are using it, and it's also the fastest JavaScript engine out there, is V8. V8 was introduced by Google in 2008 along with their browser Google Chrome. And a year later, Ryan Dial, creator of Node.js, used that V8 engine to create Node. Now, to see how he did that and how exactly V8 is being used in Node, let's go ahead and take a better look at V8. So by now we know that V8 is a JavaScript engine. Alright, let's take a look at the website of V8. So I'm going to open up my browser and search for V8 JavaScript engine. I made a typo, but it's gonna find it. Here we go. It's v8.dev. So go ahead and open it, and here's the website. So let's try to read this paragraph and try to understand more about what this V8 really is. So it says that V8 is Google's open source high performance JavaScript and WebAssembly engine. So we know that V8 was created by Google and it's open source, meaning that you could take the code, you could modify it, and you could build upon it. And we're going to take a look at its source code in just a minute. And it also says that it's high performance. Now, we said that V8 is the fastest JavaScript engine out there. And part reason that it's like that is because it's converting your JavaScript code straight into machine code. Now, yeah, I know we said that everything is going to get converted into machine code, but in the case of other JavaScript engines such as SpiderMonkey, it doesn't convert your code into machine code. What it does is that it converts your code into something called bytecode, and then a virtual machine is going to run that bytecode. So there's kind of another layer between your JavaScript and then that zeros and ones, and that is a virtual machine. That's why it's not as fast as V8. All right, let's move on. Here it says it's JavaScript and WebAssembly engine. So we already know what a JavaScript engine is. Don't worry about this WebAssembly thing. We're going to come back to it later on in the course. But basically, it would allow us to write C++ inside of our JavaScript code, which is pretty cool actually, but we're not going to talk about it right now. Written in C++. So V8 is written in C++. That's actually part of the reason that we saw that C++ code at the beginning of this video, and we're going to see more of that when we take a look at its source code. So let's keep going. It is used in Chrome and Node.js, among others. So some applications are using this V8, but two of the most famous ones are Chrome and Node.js, among others. It implements ECMAScript and WebAssembly. It's important to understand what this ECMAScript is. And what it really is that, so we have a lot of JavaScript engines out there, right? Firefox uses one, Google Chrome uses one, Safari uses one. Now, in order to create unity and consistency of the way these engines execute JavaScript code, we use a set of rules, or this ECMAScript, which is a language specification. It defines, for example, how should a function work? How should the syntax of a function of an object be like? So we have this ECMAScript so that developers, JavaScript developers, could make sure that if they create a program in JavaScript, it's going to run in the exact same way that it's going to run on these different JavaScript engines that implement this ECMAScript thing. And if you want to take a look at the specifications and rules that this ECMAScript specifies, just search for ECMAScript specification. And here's a website, ecmainternational.org. Here it says it's a language specification, and if you scroll down, you could find all of that specification either in a PDF file or in HTML. I'm going to go ahead and download this. So it's a standard, and if you scroll down to the content section, you can see that it's a pretty long file, more than 800 pages. For example, here it says how a Boolean type should be. If you click on it, here it says type consisting of the primitive values true or false. So that should be a Boolean type. So JavaScript engine that implements ECMAScript, when you create a Boolean type, it could either accept true or false. So that is what ECMAScript is. It's just a language specification that specifies how JavaScript should react, how JavaScript should be implemented. And if you're curious, you could come here and read all of these rules. All right, let's get back to the V8 website. So moving on, it says that it runs on these various operating systems and these different processors. So it runs on Windows, Mac OS, Linux, and only the devices that have one of these processors. We talked about what these are. We talked about that each processor, each CPU, could only understand a specific language. Some speak MIMS, some ARM, some IA32, and some x64. So if a processor speaks a language that is not one of these, it's not going to be able to run V8. And now, in the last sentence is where it really gets interesting. It says V8 can run standalone or it can be embedded into any C++ application. Well, let's see what exactly this last sentence means. What do we mean when we say we could embed V8 into any C++ application? And this is actually how Node.js was created. Let's go ahead and take a look at V8 source code. So what I'm going to do is to search for V8 source code. And here I'm going to open up this link in GitHub. Now if you scroll down, here it says how you could get the code. You could go ahead and clone this repository, but then you wouldn't be able to actually run it. You wouldn't be able to get a build out of it and run that V8 application. So if you want to be able to build it, get the code using gclient. I'm not going to show you how to do it. I've already done it, and I also built the project. So let's go and take a look at the source code. So here I have opened all the source code in my Visual Studio Code. And yeah, here it is. Here is all the source code that make JavaScript possible in V8. And it's a lot of code. If you come here and if you start to take a look at different files, you realize that it's a lot of code. The source, the main implementation is here in the source folder. If I'm not mistaken, it's about 100,000 lines of C++ code. So it's a lot of code here in this source folder. We also have a lot more code here in this test folder for testing the V8. I'm not sure how much, but probably more than a couple million. So we have a lot of tests written for the implementation of V8. All right, so let's take a look at the source. Here you can see different things for JavaScript. For example, here we have JSON. This is how JSON is implemented inside of JavaScript. So we have JSON.parser, and here we take a look, it's a lot of code, a lot of C++ code. Notice here I have some changes in Git. It's because I built the project and I changed some things, but it's nothing to worry about. We have, let's see what else we have. We have WASM, which is for WebAssembly. We will get to it later on in the course. Then we have objects, which is a lot of code. And notice here we have some files ending in .h and some files ending in .ccc. Both are C++ files, but .h files are header files. So in a .h file, you might define how your objects might look, how your classes should operate. And then in the .cc file, you implement those functionalities. So a .h is just a C++ file, but it stands for header file. It's a header file. Okay, then we have here some code for numbers. Then we have JSON, and we have something called deoptimizer. And if you open it, you're going to see all those processors that we talked about. We have MIMS, we have x64, we have ARM. And if you're wondering to know what is a deoptimizer, well, actually, V8 tries to optimize your code for as much as possible. But in some cases, you might do something in JavaScript which V8 might not really like. For example, if you define a variable, here I'm going to write some JavaScript. Actually, let me just create a new file. If you, for example, define a variable called a and assign a number to it, and then later on you change it to a string, V8 will do some de-optimization right here. And you could do this because JavaScript is not a statically typed language. But computers understand types. Meaning, for example, here in C++, if I could just find one file, let's see what we have here. If I search for int, you're going to see a lot of ints. So int means integer. So if you want to define a variable, you also have to specify the type. And once you do that, you cannot change the type later on. For example, this is an int type. I can't just change it later on to a Boolean type. But in JavaScript, I can, and that is not a good thing. Well, it gets the job done, but it makes your code a little bit slower. And that's one of the reasons we use tools like TypeScript. With TypeScript, you could ensure that you have static types in your application. And once you define something, for example, as string, you're not going to be able to change it later on. And that will actually improve the performance of your code. Anyway, let's move on. So let's take a look and see what else we have. Here we have the date object, the code for the new date. When you create date objects, this is what powers that functionality. We also have D8. D8 is the console for V8. So if we build all of these source codes, we're going to get one executable file, which is called D8. I honestly don't know why Google called it D8, but well, that's the name. And yeah, this is the source code. If you want, if you know C++, I encourage you to come here and play around a little bit and try to understand this V8 thing. Now, let me show you what's going to happen if I build this project and run that final executable file. So I've already done it, and I'm not going to show you how to do it. It will actually take some time. But when I built it, I got this folder called out. If I open it, I have two folders, x64 and ARM64. I got a build for x46, but my machine is not an x46 machine, so this didn't work, but this did. Let me open it in my Finder. So I'm gonna open up arm64.release. So there's a command that you can run from the root folder of this V8, and that command is actually using G++, that compiler that we saw previously. It's going to go ahead and build all of these code and give you an executable file in this out folder. So I'm going to open up this one, and here's D8. So this D8 is the final application of all of these C++ code here. And if I go ahead and double click on it, if I zoom in a little bit, I have kind of like V8 console. And I could run JavaScript. And if I run something that is not defined, I want to get an error message. And this should look familiar to you if you have used JavaScript before, perhaps in Google Chrome console, or if you have used Node.js before, you have probably seen this error. And I have access to all different sorts of things. I have access to the if statement. I could run an if statement like this. Actually, we need to specify something in the if statement. So if one, this. Notice that I don't have access to objects like documents. I can't run documents.createSelector or documents.getElement by ID. Neither do I have access to the require function. So if I run require HTTP, it's going to return an error. It says require is not defined. But the reason that we have this one in Node.js and this one in Google Chrome is because these are C++ applications that have embedded V8 into their source code. And as a result, they could now implement new functionalities and bind them to JavaScript so that you could run them in JavaScript. So let me show you what I mean. Let me show you how Node and other apps that are making use of this V8 are structured, how they are embedding V8 into their source code. So I want to open up that C++ application that we created before. So here's that file creator application that I showed you before. Now, what I could do here is to create a new folder here, for example, call it dep, short for dependencies. And inside of this dependencies folder, I might create another folder called V8. And inside of this V8 folder, I put all of that V8 source code in it. I'm not going to do it right now because it will take some other configurations and it's not really the purpose of this course. I just want you to get the bigger picture about how Node is structured. So imagine we have this folder with all the V8 source code. Eventually, what I could do is to include V8 right here. So I could say include V8. Or actually V8.h, but let's not worry about the small details right now. If I do this, if I include V8 into my C++ application, what I could do is, for example, I could come here and define a function. This is not how we define functions in C++, but it's just a pseudocode. Let's go with it. I could define a function called createFile. And inside of this function, I'm going to put in all of these logic. And also, and also right here when we create our files. So I'm going to put in all of these logic right here, and then I'm going to bind this create file using V8. So for example, let's imagine we have a function called bind, and I could say bind create file. Something like this. So I'm just oversimplifying things so that you could understand how this is working a little bit better. So when I do this, when I bind my C++ application to my V8, we might also have something like v8.bind this, something kind of like this. Eventually, what I could do then is to, in my terminal, when I run that file creator application, imagine we don't have these things, just a console. I will be able to run that create file function like this. And I might pass, for example, the first parameter, which is going to be the path, and the second one, which is going to be the content. And when I run this in my C++ application, notice that it's just JavaScript. My application is going to see it and says, okay, go ahead and run this C++ function. So I'm writing JavaScript, but actually behind the scenes, I'm calling C++ functions. And C++ is a very powerful language. In C++, I could have access to my operating system. I could deal with files, deal with my network card, and do a whole lot of things. So this is kind of like how Node is structured. They have included V8 into their source code, and they have created so many different functions in C++, and then they're binding those functions in their application so that you could, for example, call a function called require HTTP and be able to listen for requests. So you're writing this code inside of your JavaScript, but actually you're kind of making use of that C++ phase. And one more thing, when you include V8 into your source code, you're also going to be able to write JavaScript inside of your application. So I could have files like, I don't know, like app.js, and be able to run JavaScript here and make use of it inside of my other C++ files. So I know I skipped over a lot of things. There are so many configurations you have to do, and also this is not really the right syntax. This is kind of like a pseudocode, but hopefully by now you know how Node is structured. We're also going to take a look at the Node source code, and I want to show you in a little bit more details how this is kind of working. If you go to the Node website, So I'm going to go into Node.js.org. And if you go to the docs, and then here click on the dependencies, you're going to see the list of all the tools and libraries that Node.js depends upon. And right here in the libraries it says V8. And here it says that the V8 library provides Node.js with a JavaScript engine, which Node.js controls via the V8 C++ API. It's kind of like those binding things that we talked about. And here's the documentation of V8. If you click on it, it gets you straight to the v8.dev website and /docs and the documentation of V8. And you could come here and read it and get more information about how you could embed V8 into your own applications. Let's go back. So V8 is one of the most important dependencies of Node.js. We also have a couple more, but another one that's as crucial as V8 is libuv. And we're going to talk about it later in this video. So we have two important dependencies in Node.js, V8 and libuv. And libuv is also another C application. We also have LHTTP, C-arrays. These are not as important as V8 and libuv, and we'll talk about them throughout the course. We also have OpenSSL, we have zlib for compressions, and in tools we have npm to manage various different packages, install new packages. And then we have JIP, which is a build system. And notice that building is incredibly important in C++ applications because you're getting different builds for various different operating systems and different processors. And lastly, we have also gtest, which is to test C++ code. But again, let's not worry about these things right now. I just wanted to show you that here you could see all the dependencies that Node.js depends on. And two of the most important ones are V8 and libuv. Alright, so we talked a little bit about V8 and we just scratched the surface. There's so much more we could learn about V8. And we will talk about it more later in the course, but not so much. If you really want to dive deep into V8, go to their websites, read their articles and pages, grab the source code, get a build, and then maybe change a thing or two. And, just play around. Of course, you need to know some C++, but if you know, it could be a fun project. Hopefully by now you could see how great V8 and embedding it could really be. You could add your own features to JavaScript for your own needs. Maybe you want to use JavaScript to create desktop applications, games, so much more. Maybe you want to program a robot that perhaps it's a small controllable helicopter which uses an ARM CPU and runs Linux as for its operating system. Usually in robot programming, C and C++ are heavily used because of their low-level features, performance, and power. So what you could do is to take V8, embed it into your own code, and then you're going to be able to code your robot in JavaScript. Now, of course, you have to define those low-level features like controlling the speed of the wings, maybe, I don't know, with those languages like C and C++, but then you could bind those functions, and all you're going to need to do later is maybe call a function called change wing speed in JavaScript. This is one of the reasons that JavaScript is becoming more and more popular each day. People could just take one of these engines and build their own version of JavaScript. Maybe something like Node.js or React Native, something that would allow you to create new things with JavaScript. Node.js allowed us to be able to create JavaScript programs for servers, which is pretty cool. Or React Native, using it you could create JavaScript applications, but for mobile devices. And I'm sure a lot more of these things are coming into the field. Okay, now let's go ahead and grab the Node.js source code and also take a look at that one. So I'm going to open up my browser, and in the Node.js website, I'm going to go into the downloads section. And notice here, when you come here, you could either download the LTS version or the current version. I want to download the LTS version, and right here we have 3 different ways to install Node. And at the end of the day, what matters is that you get an executable file added to your path, along with some files and folders to support that file. For example, if you want to install an npm package globally, that npm package would go there. So we need to get an executable file added to our path, and actually it doesn't really matter if we don't add it to our path, but if we don't do it, each time we want to execute Node, we have to specify the full path. So for example, we put Node on desktop, we have to always say desktop slash, for example, home, and then slash node, and then we could get to the console. Now, as I said, we have three ways to download Node. We could either grab the installer, or grab the binary, or grab the source code and build it ourselves. So what I'm going to do right now is to download all these three options and then take a look at each one of them and see what we're dealing with. So here I'm going to grab the installer for my machine. So first we have to specify our machine if you're on Linux, Mac OS, or Windows. I'm also going to grab the binary. I have two options, 64 bits or ARM64. My CPU is ARM64, so I'm going to download this one as well. And lastly, I want to download the source code. Alright, so they're all done now, and now I'm going to open up my downloads folder and take a look at these three options. So this one's the installer, this one is the source code, and this one is the binaries. So I'm going to double click on this one to get the source code first. I'm going to unzip it. And I'm just going to call it node source code maybe. And now I'm going to open up my terminal and go to my downloads folder and go to that node source code and then open it up in my Visual Studio Code. So here it is. And actually, if you go ahead and clone the repository from GitHub, you're going to get the same source code. So here, for example, I have benchmark, deps, and doc. If I search for Node.js source code or Node.js GitHub, here's the GitHub link. Here we could see the exact same files, benchmark, deps, doc, and it's just like that one. So you can either come here and clone it or grab the source code from the website. All right. So right here, what really matters, and we're going to take a look here in this video. We will come back to this source code, of course, later in the course. But right now, let's try to see how V8 is used. So I'm going to open up the source folder. Actually, first, let's take a look here at this deps folder, which means dependencies. So if you open it, right here, we could see V8. We could also see zlib and UV, which is libuv, and other tools and dependencies that Node.js depends on. Those things that we saw on the website in the dependencies section. So here's V8, and if you open it, that's the V8 source code that we saw previously. So we have source, we have test, we have testing, and all of that source code that we saw in the V8 source code. Let's close this V8 and also the steps folder. Now let's go into the source folder. And right here, I'm going to try to find one of these files. Maybe, I think Node would be a good file to open up. So here it is, node.h. I'm going to open it, and I want to open the .h file, which stands for a header file. This is also the CCC file, but let's first take a look at the h file. And here, if I scroll down, I could see right here on line 63 that V8 is being included. Include v8.h. And then it's being used in different places. We'll have some bindings in place. If you go into another file, which is called, I guess it was called node bindings, if I'm not mistaken. Let's see if we could find that one. Here it is, node binding. Here's the .h file. And here the UV file is also included, which is libuv, which we'll talk about in just a minute. And also the node.h file. And in the .cc file, if you just search for bind, you're going to find a lot of results. Well, not all of it might be the things that you expect, but you know, it's binding, meaning binding JavaScript, kind of like to C++. Then let's take a look and see what else we have. If I scroll down, here we have a lot of files for streams, which we're going to take a look at. We have TCP, UDP, util. We'll take a look at all of these later on. We have timer functions like set timeout, set immediate, Then we have the implementation for workers, which is another important thing that we have to talk about, zlib, and so much more. We have node performance, files, and so yeah, a lot of things are going on here. So let's close this source folder. We have crypto. We'll also take a look at this crypto. It's an interesting package. Okay, let's close the source, and notice here, if you come to the lib folder, you're going to see a lot of JavaScript files. Now these are also implementation for Node.js, meaning there are the Node.js source code, for example, cluster, buffer, search, which this assert we use to test Node.js code. Notice that they're written in JavaScript. And if you recall, previously we said that if you include V8 into your project, into your C++ project, you're also going to be able to write JavaScript. So this is why we have a lot of JavaScript code here in the Node source code as well. Source code for HTTP, for DNS, for the FS module or file system, for net, OS, path. All of these are super important, and we have to talk about all of them in the course. And when you include a module, like for example, you say const fs equals require fs, you're actually including these files. So if you run this line, you're actually including this fs module. And right here, it is somehow binding to that C++ file. So if you search for binding, here you can see a binding, internal binding fs. And it means that it goes to the C++ phase and handles your file requests. We'll take a look at these in more detail later in the course. All right, so this is the Node source code. And what you could do is to build this source code. So if you come back to the website, and if you scroll down, here it says building Node.js from source on supported platforms. And if you open it, it explains how you could build all that source code on your device. So you have to use make, which makes use of that G++ compiler that we saw previously, and yeah, you could run a whole bunch of commands, and then ultimately you're going to be able to get that binary executable file that you could add to your path and be able to run Node. Alright, so that's it about the Node source code. Now let's go ahead and take a look at other files that we downloaded. We have this Darwin RM64 file, which is the binary file of Node.js. So if I double click on it and unzip it, and if I open up the folder, right here, if I go to the bin, you could see that Node executable file. So I could double click, I get access to the Node shell, so I could require various different packages like this. And what happens when you install Node is that you kind of add this node into your path. And you could also install Node just like this. All I need to do is to grab this and put it somewhere that my path would understand. And we also have this lib folder and a couple more that are supporting that executable file. For example, if you install a new global package, it's going to come into this Node modules folder. This is one way you could install Node. And notice I said you don't always have to specify the path. So I could just come here. If I could open my terminal right here, and get a directory, what I could do is to run Node.js from this path. So I could, for example, from my root folder, I could say this, and I want to be able to get to the shell. Or I could run files like that. So for example, I might have this and then .server.js. So when you install Node, what you're actually doing is that you're getting this executable file along with these supporting files added to your path. So if I run this installer, what it does is that it takes those binaries and it adds them somewhere that my path would understand. So here it says this package will install Node.js version this to user local bin/node. So this is my path folder and npm in user local bin/npm. And this folder bin/npm is just this one, bin/npm. Notice it's an alias or a shortcut. So if I show the original one, here it takes me to that lib folder. So lib node modules npm and then bin. The way we installed Node was using nvm. So if I run which node, here I get the path that my node executable file is located. So I'm going to open it. I'm going to open the folder. And here I have the same bin folder. I have Node, I have npm, and a couple more packages that I installed globally, like pm2 and rush. But if I go back up, I see that lib folder here again. So node modules, and then pm2 and npm, and other packages that I installed globally for my Node version 14. If I go up a level again, I'll see different versions that nvm installed. If I go into version 16, again I have that bin and then the Node executable file. So this is kind of what happens when you install Node.js on your system. Node.js is just a C++ application, so you could also come here and build all of these source code yourself and then get that executable file and add it somewhere that your path might understand. Right, so that was a deeper look at what happens when you install Node.js on your system. Now before we get into libuv, I just want to take a moment and tell you some history about JavaScript and Node.js. Just a little history about Node and JavaScript. Nothing too crazy, nothing too memorize or anything like that. Just some history for fun. And then after that, we're going to talk about libuv, which is going to be the last topic of this video. All right, here we go. So about 90 years ago, the first computer was invented. These computers were those huge ones that used light bulbs to represent zeros and ones, or on and off switches. They occupied a whole room and they would consume a whole lot of energy just to be able to do some simple calculations. And the way we used to program these were actually just by writing straight binary code, just zeros and ones. Then some programming languages came in to make this easier, and one of the most important ones was assembly. That came in the year 1949, which made the job of programming for these computers a lot easier. Now, about 20 years later, the first high-level programming language was created, the C language, which really had a great impact in shaping the computers and software. And it was considered to be the first human-readable programming language, something that its syntax was more like English, like those while and if statements. Now, C++ is considered to be the new version of C, which was published in the 1980s. In the year around 1977, the first personal computer was introduced to the public, which was Apple I. Now, a couple years prior to that, there were also some other personal computers out there, but they were more like hobby projects, rather something that regular people could buy. When Wozniak and Jobs introduced Apple I and Apple II, it really started to revolutionize the personal computer industry, and computers became way more widespread among people. When Bill Gates introduced Windows about 10 years later, computers became even more popular. Then the internet was invented in the year 1983, and a couple years later, the first website was launched at 1991, which at the time only was a very simple web page, just some simple HTML. JavaScript was introduced by Brendan Eich in 1995 with the purpose to make web pages interactive and be able to program them. In that same year, Internet Explorer was introduced by Microsoft, and later that year, the second version of it was published, which supported JavaScript. And then more and more JavaScript engines started to appear. The ECMAScript specification was defined 2 years later in 1997 to make sure that developers could make sure that their JavaScript could run as expected on different browsers. Firefox was published in the year 2002, and it was and still using the SpiderMonkey JavaScript engine, which was the first engine. Then Chrome, along with its engine V8, was introduced in the September of 2008. And then a year later, Ryan Dial took the engine and created Node.js to make the job of creating network applications a lot easier, faster, and more scalable than other solutions that existed. And it was somewhere around the year 2012, I'm not quite sure, was it 2012 or 2014, that V8 developers started to take Node.js into account so that they wouldn't push an update if it would break the Node.js tests, which was a huge deal for Node.js. It really made the growth of Node.js faster and better. Previously, for example, Node.js wanted to give a new update, but they wouldn't be able to release it because the new version of V8 would break their tests. So there were some problems with Node.js and V8. They weren't really compatible, but now it's way better than before. All right, so that was just a little bit of history about Node.js, JavaScript, and some of the things that had an impact on it. Now, it's just a very simple history. Now, a lot happened behind some of these items I talked about. For example, if you read about how the first computer was created and how the personal computer industry started to took off, it's actually a lot. So this was just a really brief history, and now we're ready to talk about one of the most important dependencies of Node.js, libuv. I really couldn't end this video without talking about some of the crucial aspects of Node to understand: libuv, event loop, and event-driven programming. And we're going to talk about them right now. If you recall, we said that Node.js is meant to be a system language, and its purpose is to create network applications. In other words, it's a server-side language. Now, if you think about it, a server-side language needs to be able to do some things that JavaScript couldn't do. So, you know that Node.js is a C++ application that has V8 embedded into it. So let's think about some of those features that Node.js needs to add to JavaScript in order to be able to be a good server-side language. For example, it needs to be able to talk to different processes on a computer. One of them might be a database server like MySQL. Node.js needs to have a way to be able to talk to that database server to fetch data from it, or to write data on that database server. Another example would be to be able to deal with files. It's really important for a server-side language, a server-side technology, to be able to have a way to deal with files. It needs to be able to handle file uploads from the clients, or be able to read a configuration file when it's starting, or be able to, for example, save the logs of the server on a file. Another feature that it needs to implement is scaling. It needs to be able to handle millions of users, millions of requests at the same time. Now, Node.js is incredibly scalable, and we're going to see that later in the course. And of course, it needs to be able to deal with network requests, be it a TCP request or a UDP request, accept some requests from a port, or send requests to different various URLs. So an ability to handle network requests is also another very important thing that Node.js needs to implement. Now, a lot of these things that I talked about are done using libuv. So libuv is handling all of those things behind the scenes. libuv was written in C by the creators of Node.js, but now it's actually used in various different projects. So let's go ahead and take a look at the Node.js website and see what it says about libuv. So I'm here on the Node.js documentation website in the dependencies section, and I want to scroll down to find the libuv section. So here it says that it's another important dependency of Node.js, and it's a C library. Now, notice that C is just like C++. C++ is considered to be the new version of C. It added some new features like object-oriented programming. So you could just write C in your C++ applications, and it would compile just like before. So C is just like C++, and it's not really our discussion to talk about their differences, but think of it like C++. All right. Now, for the rest of the paragraph, you're going to see a lot of words that you probably don't know, like non-blocking I/O, DNS, child processes, pipes, signal handling, pooling and streaming, thread pool, and it would be an overkill to talk about all of these things in this video. What we're trying to do here is to lay a foundation of knowledge about how Node.js is working under the hood. So for this video, we're not going to talk about what these are, but they're actually describing what this libyv is doing. For example, pipes. A pipe is actually, like the name suggests, it's a way of communication between two processes. So I might have Node.js and a database server opened up on my machine. There needs to be a way of communication between these two processes, and those are done using pipes, and it's done at the operating system level. And if you're wondering to know what processes are, if you go ahead and open up your activity monitor on Mac, or if you're on Windows, open up your task manager, or on Linux, just open up terminal and run the top command. When you do that, you're going to see the list of all the processes that are opened up on your computer. Now in my case, I have 335 processes opened up on my computer. So if I count all of these items, I'm going to get that number. Alright, so these are what processes are, and if you run Node.js, you're going to get a new one right here. Or if you start your database server or your Redis server, you're going to get a new process right here on this list. So for example, if I just run the node command, I want to get a new process. I could just search for node, and here it is. I see the node process. The process name is node. And there are also some other important things about this process that we need to identify, and we'll talk about it more later, like the CPU usage or the number of threads that it has opened. Don't worry if you don't know what a thread is. It's going to be its whole new discussion, and we're not going to talk about it right now. Another important thing is PID, or process ID. It's a unique ID for each process opened up. For example, if I want to kill this process, I could just open up my terminal and run kill and then the process ID, and it's going to be able to kill this process. Or the amount of memory that it's using. If I switch to the memory tab, I could see how much memory this process is using. In this case, it's only 9 meg. But if I go ahead and create new, for example, buffers and allocate new memory, this number is going to go higher and higher. Another one is in the network tab. I could see the number of bytes that it sends out and the number of bytes that it receives, and also the number of packets that it received and sent. Again, we're going to talk about these later. Right now, all we're trying to do is to really understand what happens when we run Node and when we execute a command or listen for an incoming request. What is really happening behind the scenes when we do that? So let's now take a look at a diagram and see what really happens when you start your Node process and you run a piece of code. So your computer that runs Node.js, either it's your own personal computer or it's a server in the cloud, doesn't matter. It has a CPU, a RAM, storage, and a network card. So that computer has this hardware. Now, there are also some other hardware involved in a computer, like a graphic card, or we could also talk about things like keyboards or a monitor, but really Node.js doesn't deal with those things. So we have these 4 pieces of hardware, and if you're wondering to know what is a network card, it's the thing that allows you to connect to the internet, or by maybe an Ethernet cable or Wi-Fi or a 4G or 5G connection. Really, it could be anything, but this network card would allow you to connect to the internet or just connect to different computers. So you could have 2 computers side by side and you could connect them together using an Ethernet cable, using a network. Now, on top of this hardware, we have the operating system. Now, think of an operating system like a way of communication between a program, a process, and your hardware. It's something that controls everything on a computer. It allocates resources to different processes and allows them to be able to communicate with each other. or it will allocate some amount of RAM, some amount of memory to a specific process, or it will go ahead and fetch some data from the storage. Maybe it's an SSD drive or a hard disk, doesn't really matter. The operating system goes ahead, fetches that file, and then it gives that to a process. So we have a way of communication between programs and hardware through operating system. Now, on top of our operating system, we have our process, Node.js. Now, we might also have so many other processes running in our operating system, like a MySQL process or Redis. We saw that my computer I had opened up more than 300 processes, and in yours it's kind of like that number. Naturally, a lot of these processes are opened up by the operating system itself, but anyway, let's now put our focus on Node.js and not focus on the other processes. So what exactly is happening inside of Node? We saw that we have the V8 engine, which allows us to interact with the Node application through JavaScript, which is pretty cool. And we also have the libuv package, which Node.js uses to handle things like file system, like creating files, deleting files, writing files, and also it handles the network things like sending requests, listening for requests, socket applications, and a couple more things. Also pipes and talking to other processes. And these two are the most important things inside of Node.js, two of the most important libraries that Node.js depends on. Now we also have some other things like LLHTTP or zlib, OpenSSL, and CRs, but really we're not going to focus on them right off the bat right now. We will talk about them later in the course. For example, we're going to talk about zlib when we're talking about compression, or we're going to talk about OpenSSL when we want to talk about crypto, hashing strings, and all that kind of good stuff. But right now, these are not really as important as V8 and libuv, so let's put them aside and really focus just on these two things. Now, there's also another thing inside of Node that is crucial to understand, just like V8 and libuv, and that is called event loop. Now, event loop isn't another package or library that Node.js has inside of its dependencies. It's something that Node has implemented with the use of V8 itself and libuv and all of that C++ code that we saw that Node.js has. So what does this event loop do? And exactly how does V8 event loop and libuv kind of interact with each other to be able to get this Node.js thing up and running? So let's take a look at an example. So let's say that we have this code, two constant logs and a for loop that's going to run for some time in between them. Let's see what's going to happen when we run this code. So here I have my console, and Node.js or V8 executes code in a synchronous manner, meaning that it's going to start from the top and it's going to go all the way to the bottom of the file and execute every single line of code. So that is happening inside of a single thread. So here's what's going to happen. It's going to start from the top, it's going to see the constant log, and it's going to log first onto the console. Then it's going to move into the for loop. Now this for loop is going to run for about, how many is it? For about 100 million times. So it's a huge for loop that's going to probably take a couple of minutes to complete, or a couple of seconds. And what's happening inside of this for loop, just imagine it might be some calculation that might take some amount of time. Maybe it's hashing a string or modifying a string, really doesn't matter. The point is that this for loop is going to take a couple of seconds or a couple of minutes to complete. So here's what's going to happen. V8 is going to keep executing this for loop without even paying attention to this console log. So what happens is that my application would be blocked until this for loop finishes. So it's going to keep executing this for loop over and over again for 100 million times, and then once it's done, it's going to move on to the last log and log second to the console. So the important thing to understand here is that while this for loop is running, my whole process, my whole Node.js process would become unresponsive. I can no longer go ahead and fetch a file from my storage, or I can no longer respond to an HTTP request or send a request to the outside world. I can't even log a single string to the console. So my whole process will become unresponsive until this for loop finishes. Now, unless you have set it up multiple node processes, or you're running this for loop in kind of another thread, which we're going to talk about, your whole application will become unresponsive. So your whole site would go down until this for loop finishes. Now, definitely when you're running Node.js in production, you have got to scale it. You have got to use some asynchronous techniques, which we will talk about all of them in the course. I know I've said that sentence for hundreds of times now, but really, you can't do that inside of a single process. If you do, your whole application would just stop working. So this is what happens when you execute code synchronously. Now let me show you this example inside of my code editor as well. So I have created a single app.js file on my desktop, and I want to open up my code editor and also my terminal. So what I want to do is to run that console.log first, and then a for loop. For let I equals 0, and then let's run it for, I don't know, 100 billion times. So 100 billion times. Guess we need another 3. Yeah, another 3. Now we have 100 billion. And I want to increment I by 1. And actually, I'm not going to do anything inside of this for loop. Incrementing I by 1 for 100 billion times is going to take a couple of seconds. And then I'm going to put the last log right here. So console.log second. And I'm going to run this code. And when I run it, I'm quickly going to get this first command. And I missed this R. So I'm first going to get this first log onto my console, and then it's going to wait for a couple of seconds. And when it's waiting, and it's doing this for loop, my whole application will become unresponsive, and this log is not getting run. So here's what's going to happen. I run it, I get the first command, and while it's doing that for loop, if I take a look at my activity monitor and I search for Node, notice here that its CPU usage has jumped to 100%. And it cannot really do anything else. It is running in a single thread. Now here, if you take a look at the number of threads, we have a couple of threads, but we're going to talk about in just a minute why it's happening. So my whole application is now unresponsive, and I cannot do anything else unless this for loop finishes and V8 moves on to the next line of code. Okay, so what does this exactly mean? Does this mean that Node.js is this awful technology that could only do one thing at a time? Does this mean that when I want to read a file or respond to a request or fetch something from the database, my whole application will become unresponsive? Well, actually, quite on the contrary. Node.js is incredible at doing those things by allowing you to execute code asynchronously. And that's possible by things like event loop and libuv. So here's how it works. For example, you want to read a file. You tell from V8 to libuv and event loop that I'm gonna read this file. Okay, so you go ahead, you go ahead and read the file, fetch the file, do everything that you gotta do. And while you're doing those things, I'm gonna continue on with my code execution. I'm gonna continue in my V8 thing and execute the rest of the code. And when you're done, let me know somehow so that I could respond. So that, for example, I could, when you're done reading the file, you give me the data, and I might, for example, log it to the console, or I might give you another task to get that data and create a new file with it. That probably doesn't make a good sense to you right now, so let's get back to our diagram, and let me show you exactly how does that work. So here's our node process again. We have V8, the event loop, and libuv. Now let's say that we have this piece of code. A console log, and then reading a file, and then a log after the file has been read, and then a final log, which is the third log. Now, Node is going to start to execute this code from the beginning. So it's going to see the log, and it's going to log the first to the console. Then it's going to move on to the second line. So here's where it gets interesting. Node.js is going to see this line of code that it says, okay, require the FS module and then read this file. Now, when you're doing this, when you're requiring the fs module and then calling this read file function, if you recall, we're actually requiring the fs.js file from the lib folder in the Node.js source code. And in that file, we had those binding things, those things that would kind of allow us to talk to the C++ face. So Node.js is gonna see this line, and then it's gonna push an event to the event loop. Now this event loop is the stack. You could push new things on it, and it's gonna keep running them in a loop until they're done. And when it happens, when Node.js pushes something into the event loop, it's going to quickly continue on with the rest of the execution, and it's going to log the third command. Now, while the rest of the execution is undergoing, the event loop is also doing its thing. And the event loop is running these events one by one in a loop. So it's constantly going to check to see if it has something on the stack, if it has an event to attend to, and if it does those events and it's done, it's going to quit. So Node is going to push something into this event loop, and that event loop is going to see, okay, I have to read a file, so it's going to go ahead and talk to the libuv. It's going to tell the libuv, here's the file that I need you to fetch. Here's the path, and here's some more configuration. For example, and we might want to get it in a binary format, or we want to get it in a string format. So we're going to tell libuv that go ahead and fetch the file. So libuv is going to reach out to the operating system, and then the operating system is going to go to the storage, your hard drive, and then fetch that file, and then give it back to the Node.js process. Give it back to the libuv to process it. And once libuv is done with processing it, it's going to give it back to the event loop, and then the event loop is going to see it and says, okay, the job is done, whatever libuv had to do, it had done it, and now I'm ready to notify the source code that here's the data, and you go ahead and do your own thing. So it's going to give that data to this V8, and it's going to see it and execute this callback. And now the event loop is done, so we no longer have anything in the event loop. So the event loop is completely done, and now the V8 is going to execute that callback like this. And when it's done, we're no longer going to have anything in the V8, and we also no longer have anything in the event loop, so the Node.js process is going to exit. This is what we call an event-driven programming, meaning that you're writing your code, and then inside of that code, you're kind of issuing different commands, issuing different events. For example, here you're saying, okay, go ahead, read this file, and then you're going to continue on with the execution. And then when those magic happen behind the scenes, and then the file is fetched and read, you're going to execute a callback responding back to that event. Now, what are some of the things that we call an event? Actually, there are a lot, and we're going to see a lot of them throughout the course. Reading files is one of them. Timer functions, the HTTP module, doing things related to network in general, and actually a lot more. Now, let me show you a couple more examples to really try to solidify this knowledge. So you have probably seen patterns like this. So we might have a log function called A, and then I want to say B, C, D, and F. Let's just keep it at this. And then I'm going to put one of these logs inside of a setTimeout function like this. setTimeout constant log. And for the time, I'm going to specify 0. If you're not familiar with the setTimeout function, we have a video dedicated to talking about these timer functions, but basically it's going to see the code and execute it after some amount of time that I'm going to specify here in milliseconds. So for example, if I say 1000, it's going to execute this constant log after 1000 milliseconds. But what if I put 0? What's going to happen in this case? What do you think is going to happen? In what order we're going to get these A, B, C, D, and F? Let's go ahead and run it. So node app.js. When I run it, I get A, but notice that now instead of getting B, I'm getting C, D, F, and then at the end, I'm going to get this B. Why do you think this happens? The reason is when you're running a timer function like this, you're actually calling the event loop. You're putting something onto the event loop. So your code is going to start to execute from line 1. It's going to see this timeout function, and then Node is going to push a new event onto the event loop after it sees this set timeout function, and then it's quickly going to continue on with the rest of the application. And then once all of these are done, the main execution is done, it's going to execute the callback function relating to that event. Actually, we have something dedicated for this purpose in Node, and that's called process.nextTick. And if I run this, I want to get that same result, A, C, D, F, and then at the end, the B. So this process.nextTick, what it does is that its only purpose is that if you want to run something after your main execution is done. And it really comes in handy from time to time. And we're going to see some of its use cases in the course. But the point is, when you're doing this, you're pushing a new event onto the event loop, and then the rest of your application is going to get run. And then once done, this line is going to run. Now also remember that we said for as long as we have something in the main thread, in that V8 thing, or in the event loop, our Node.js is going to run. And whenever we have nothing in those two things, Node is going to exit. So if I just have one constant log and it's just one, so something like this, Node is quickly going to run it and then it's going to exit and I'm back at my desktop. But if I do something silly like this, so I say set interval, and I just run this for hundreds. Now, if you're not familiar with set interval, what it does is that it executes this function every this amount of time. So it's going to execute this code every 100 milliseconds. And now I'm not going to put anything inside of it. Now, if I run this code, so node.app.js, it's not going to exit, and it's going to keep going and going. If I take a look at my activity monitor, I search for Node, here I have it. And it's not actually using any amount of CPU. It's only using less than 1% of the CPU usage. So what's happening right now, I'm pushing something onto the event loop, and I'm not exiting. So as long as we have something in the event loop or the main thread, that V8, Node.js is going to keep running and running. Now, in the previous video, when we created a simple web server, that is exactly what's happening. When you're listening for a specific port, you're adding something onto the event loop and you're not actually deleting that event. It's gonna keep being there until you hit Control-C. So the event loop is gonna constantly watch out for new requests onto that port, and whenever a new request comes to that port, then libuv is gonna get that, and then it's gonna tell event loop, and event loop is gonna call that callback function that is there to handle the requests. Now also it's very important that you never block the event loop or the V8 or the main thread. So what I mean is, if we take another look at this one, this V8 thing and this event loop, they are both running in a single thread. So think of this little green rectangle as a thread. And if you don't know what a thread is, we're going to talk about it in a lot more great details later in the course, but think of a thread as an execution line, something that could only execute one thing at a time. So for example, in case of a PDF viewer, if this application, this PDF viewer is only running in a single thread, and you search for something while the search is going, you're not going to be able to, for example, highlight a text or go to the next page. Because the whole application is in a single thread, when you occupy that thread, when you kind of block it by that searching thing, the whole application will become unresponsive. And you could fix it by setting up multiple threads. So one thread might handle the searching thing and another thread might handle the rest of the application. So here we have the V8 and the event loop in a single thread. So if you block each one of these, your whole application will be unresponsive. Now in Node.js we have a couple more threads in the libuv, and they're called thread pool. And by default, we have 4 threads right there. And these handle some things like the file system. So when you want to create a file or handle files in general, this thread pool would kick in and handle that thing. Now, as I said, by default, there are 4 of these, but you could increase them using a flag in your terminal. Again, don't worry too much about thread pool and this threading thing. We have a whole discussion talking about these things like clustering child processes, setting up multiple threads, and a lot more. Now, not all of the other tasks that are assigned to this libuv are done using thread pool. For example, network requests aren't done using thread pool. Actually, Node.js is doing its best to minimize the use of this thread pool for as much as possible. So whenever it can, it will reach out to the operating system and do the things asynchronously. So when you, for example, listening for requests, the requests would coming through the internet, through your network card, and then it goes from the operating system straight to libuv, and without touching this thread pool, it's going to go straight to the event loop and then V8. But some things are handled using this thread pool, like dealing with files. And this thing that Node.js is using, trying to minimize the use of threads, is what that makes Node.js incredibly scalable and incredibly fast. Because it uses very little amount of threads, so you could really scale it well without using a lot of hardware resources. Now again, we're going to talk in much greater details about what not to do to block this thread pool or to block this main thread. But let me just show you one example and illustrate what I mean when I say you should never block the event loop or the main thread. You should always watch out for those things. So I'm going to go back to my code editor. And here, I'm going to set up a setTimeout function. And this setTimeout function is going to run after, let's say, 50 milliseconds. Like this. And I'm just going to do simple log. So console log done. Now, if I run this, you expect what's going to happen. After a very short amount of time, I'm going to get done. Almost instantly. I don't even have to count. So as soon as I run it, I'm going to get this done. And remember again, when we're running this code, as soon as Node.js sees this timer function, this setTimeout function, it's going to push a new event onto the event loop stack. And then it's quickly going to continue on with the rest of the code execution. So here's the rest of the code, and the event loop is going to see this line, push that event, and then quickly continue on with the rest of the code. And after about 50 milliseconds, we expect to see this line kick in. But what if I do something like this? So I'm going to put in a for loop. So for let I, starting from 0, going to, let's say, 1 billion. So 1 triple 0, triple 0, it's 1 million, another triple 0, and now it's 1 billion, I plus plus. Now, what do you think would happen in this case? Do you think that Node.js is going to continue with this execution and after 50 milliseconds is going to move on to this line? Or do you think that the whole application would just stop? What is really your guess here? So think about it for a minute. Okay, so let me now execute this program and see what I'm going to get. Now remember that previously when we ran this node app.js, we instantly got this done message. Now what's going to happen in this case? So I'm going to say node app.js. And if I run it, notice that it took a little bit longer amount of time before I get the done message. To make it a little bit more clear, I'm going to increase this number to 9 billion. Let's run it again. And I'm going to change it to only 1 millisecond. So as soon as I run this node app.js, I should instantly, without even waiting for the shortest amount of time, I should get this done message. So let's see what's going to happen. As you can see, my application is now blocked. So when Node.js is executing this for loop, and notice that now I got this done message, but a lot longer after only 1 millisecond, it was a couple of seconds. So what happens in this case is that I'm blocking that thread. So the thread is now occupied. It's constantly trying to increment this I by 1. So that whole thread will be blocked. And this event loop thing cannot even kick in. So if I'm, for example, doing some heavy calculations here using that thread pool, like dealing with a file, until this for loop is done, I'm not going to be able to execute that line. This is what we mean when we say do not block the main thread or the event loop. And we're going to again talk about it in a lot more great details later on in the course. Now, if you go to the Node.js documentation, so I'm going to go into nodejs.org website, and then I'm going to go to the docs section, and right here I'm going to click on the guides. And if I scroll down a little bit, in the Node.js core concept section, you will find a very, very crucial article. I can't really say enough how important this article is. It says don't block the event loop or the worker pool, aka the thread pool. So this article is a little bit more advanced, and definitely I don't expect you to come here and read it and understand it, but we will, of course, talk a lot more about this. It actually discusses in great details about what we talked about, how not to block the event loop or the thread pool. Now here, for example, it is talking about some of the vulnerable regular expressions that if you run, for example, an attacker might be able to give it something that is going to occupy your whole process and your whole application will become unresponsive. There are some important things that you need to watch out for to avoid attacks like denial of service and a lot more things that you need to really watch out for. For example, there are some things like the synchronous functions. It's going to be way better to, instead of using this sync functions that are doing that thing synchronously, use the async versions. And again, we will talk about all of these in great details. Here, for example, you're seeing some complex calculations examples like partitioning using a for loop. And yeah, here it says some examples about offloading. Again, I don't really expect you to understand anything about these, but I just wanted to tell you that there's this very important article in Node.js, and we will come back to this later on. Okay, that was it about this long video, and I know that I threw a lot of information at you. We talked about JavaScript engines, V8, some C++, assembly, libuv, event-driven programming, asynchronous code, and more. And honestly, I don't expect you to fully understand everything that we talked about here. This video wasn't really meant to teach you things like the libuv itself, or the V8 or C++, rather to give you a feel of what Node.js really is. And hopefully by now, you're not saying that Node.js is another JavaScript library or framework like React, Angular, Vue, or jQuery. Node.js is a lot more than that. Those libraries are just JavaScript. They're written in it. Node.js understands JavaScript. It's a lot more than just JavaScript. It has added a lot of new features to the language in ways that we talked about. Now again, don't worry if you didn't fully understand some of the things that we talked about. We will definitely talk about the things like the libuv, asynchronous code, how not to block the application, and a lot more later on in the course. We also have to talk about scaling and important things like security, clustering, and so much more. And truth be told, I really oversimplified some of the topics we talked about here, like that diagram with hardware and libuv and that V8 thing inside of it. We will come back to that thing and make it more accurate when the time is right. When we're talking about some specific things, we will make that more accurate and make it better and better. So we have a lot of things to do and a lot of things to learn. So let's keep going. I'll see you in the next one.